So next is colored ions, colored compounds. See, transition metals are well known for providing colored compounds. All of you know, in fact, they are adding color to chemistry, right? So the unpaired electrons present in the d orbital is able to cause excitation, de-excitation of the electrons by absorbing suitable wavelength of radiation from the white light and is able to give color. All of you know that. So it is basically due to presence of unpaired electrons, and the DD electronic transition is the general simple reason for the color performed in transition metals. Quite naturally, when there is a D0 electronic system, we don't find a colored compounds. D10 electronic system, we don't find a colored compounds, right? Usually, most of the compounds are giving color due to excitation, de-excitation of electron through the d orbitals, and that can be explained by the contribution of ligands in a complexing system, which we are learning in complex chemistry. If you take simply aqueous solution, water molecules will act as ligand. Ligands are basically a reason for explaining color for the molecules. Okay. You see some of the colored compounds which are given in the textbook, table 8.8. Very simple and evident to understand. A D0 system, scandium 3 plus, is colorless. A D0 system, scandium 3 plus, D0, which is colorless. You see again D0, titanium 4 plus is colorless. So D0 system, similarly D10 system will be colorless. You can see at the end of the table, D10 system, maybe it is given. Yes, D10 system, zinc compounds. Zinc compounds are colorless. While other systems where there is unpaired electron, say D1, D2, D3, etc., are colored in nature, and get familiarize yourself with the color of various transition metal compounds available. For example, Fe2 plus is green in color, Fe3 plus is yellow in color, manganese 2 plus is pink in color. Most of the things all of you know. Copper well known giving blue colored solution. Copper well known giving blue colored solution. Nickel well known for giving green colored compounds. So try to familiarize with the most commonly encountered system of ions and its compounds and its colored nature. So among the various atomic physical properties of transition metals, one of the highlighting property, it is color, no doubt. Variable oxidation state, catalytic behavior, and so much of that kind of property. Color is an important property of transition metals, right? So that lands one of the next atomic and physical properties, color. You must go through that details. Formation of complex compounds. Formation of complex compounds. Complex coordination chemistry. We are learning another important chapter. The very next chapter to D and F block is coordination chemistry. Right? Coordination chemistry greatly devoted towards the contribution of transition metals. Transition metals are mainly contributing various complex molecules, coordination compounds, all of you know. A few examples are given. Complex compounds, those which the metal ion bind a number of anion or neutral molecules, act as ligands. Anion or neutral molecules act as ligands, and overall complex species are obtained. These are a few examples of complex molecules. Ferrocyanide, ferricyanide, cuprammonium complex, platinum chloride, etc. Very important and popular complex molecules are there, which in detail dealt in the particular chapter. Anyway, that is another important property of transition metals, to perform complex compounds. Right. And what is the major cause of exhibiting such a complex molecules? Comparatively small size of the metal ion and their high ionic charge. and the availability of d orbitals. 3 points we can highlight according to the textual content: small size of the ion, high charge of the ion, and availability of d orbitals. Why the transition metals are able to perform complex compounds? The major 3 points we can highlight as it is quoted in the textbook. Next is catalytic activity. Catalytic activity. Transition metals are well known for their catalytic behavior. Various examples we can see. Vanadium pentoxide act as a very popular catalyst in contact process, preparation of sulfuric acid. Then finely divided iron used in Haber process. All of you know nickel used in catalytic hydrogenation reactions. Powdered nickel used. These are few examples. Catalyst at a solid surface involve formation of bonds between reacting molecules and the atoms of the surface of the catalyst. So the basic idea behind or basic science behind the heterogeneous catalytic activity, all of you know and learned in another chapter, surface chemistry, it is adsorption. Adsorption theory is explaining the mechanism of catalytic activity in heterogeneous catalysis reaction, and that is what highlighted. So there is an increase in concentration of reactant on the catalytic surface and also weakening the bonds in the reacting molecules. Activation energy is lower. When you take hydrogen in nickel, hydrogen come and adhere to the surface of the nickel. So what will happen? Since there is a bond formed by H2 molecule on the surface, it will weaken the HH bond. HH bond will be weakened. Thereby, the activation energy is lowered and is able to take part in the chemical reaction. Right? Also because the transition metal ions can change their oxidation state. So not only adsorption, one point of catalytic activity. Those who remember adsorption theory, modern adsorption theory, it is a combination of old adsorption theory dealing with the surface activity and intermediate complex formation theory, which is contributing or explaining about the variability in oxidation state. So modern adsorption theory is contributed or explained by the adsorption phenomenon, not only adsorption phenomenon and hence the energy related facts, not only that, but also the complex formation, intermediate transition formation by variable oxidation state. For example, a demonstration is given how Fe3 plus ion act as a catalyst in the reaction between iodide and per-disulfate. How per-disulfate reacting with iodide giving iodine and sulfate. That reaction, how Fe3 plus involved in the catalytic action. It is demonstrated in the textbook, a very interesting example which you can see how this reaction is taking place with the help of Fe3 plus. You see Fe3 plus interacting with I minus and Fe3 plus is reduced to Fe2 plus and I minus is oxidized to iodine. So Fe3 plus Fe2 plus switching help iodide converted to iodine. Agreed. Now that Fe2 plus interacting with the per-disulfate and Fe2 plus is oxidized back to Fe3 plus and this is converted to sulfate. In fact, we have to justify the point in such a way that I minus is not directly interacting with the per-disulfate. I minus is doing the business with the Fe3 plus. And itself it is converted to Fe2 plus and I minus becomes I2. And now that Fe2 plus ferrous is interacting with the per-disulfate, where Fe2 plus is oxidized back to Fe3 plus and coming the quantitatively and qualitatively Fe3 plus is back. All of you know what is meant by a catalyst. A catalyst quantitatively and qualitatively remain unchanged at the end of the reaction. All of you know that. So here we started with Fe3 plus, we land with Fe3 plus. And in between it is switching between Fe3 plus to Fe2 plus and interacting with the people concerned and the reaction is proceeded. So such kind of activity is a major reason for the catalytic explanation of the transition metals. The other point already commented, adsorption. The gaseous molecules or reactant molecules come and absorb over the catalytic surface and thereby the reaction proceeds. So that is about catalytic action. And the next is formation of interstitial compounds. Formation of interstitial compounds. That is the next point. That is another highlighting point of transition metals. How they form interstitial compounds. Many times they may be non-stoichiometric also, right? See, they are making interstitial compounds, particularly with small atoms like hydrogen, carbon, nitrogen. They seem to be like trapped inside the crystal lattice of the metal. They are usually non-stoichiometric in nature. Many of the compounds are non-stoichiometric in nature. What is meant by non-stoichiometric? Non-stoichiometric means which does not follow a fixed composition, varying composition. That is non-stoichiometric compounds. Many compounds are non-stoichiometric in nature. This is non-stoichiometric compounds, right? Mainly involving with hydrogen, nitrogen, carbon, etc. They are neither typically ionic nor covalent. We can say they are typically ionic or covalent, right? Sometimes non-stoichiometric also. Correspond to any normal oxidation state of the metal. You can find like a normal oxidation state of the metal. It can be a mixture. It can be some defect, like what we are discussed in defect, metal excess, metal deficiency defects, etc. Like that, right? They are called interstitial compounds. Interstitial compounds. There was an old entrance exam question regarding the principal physical and chemical characteristics of interstitial compounds. It was so given the same points from the NCERT, option A, B, C, D. And they ask you which of the following, it was the question, like original question, you can trace and find out. Which of the following is not the characteristic property of interstitial compounds? They have given high melting point, higher than pure metals, which is a true statement. Very hard, some borides approach a diamond in hardness, metal borides. Some borides are extremely hard. They retain the metallic conductivity. And one choice they have given, they are chemically highly reactive. That is an incorrect statement. And the question was like that. Which of the following is the incorrect statement pertaining to the characteristics of interstitial compounds? They are chemically inert. So they are high melting. They are very hard. They retain the metallic conductivity. And they are chemically inert. That is the characteristic behavior of interstitial compounds. Right? Now, another important property known to all, alloy formation. Alloy formation. Transition metals are well known for their alloy formation. They blend with other metals forming alloys. It can happen with the two types, interstitial alloys or substitutional alloys. Interstitial alloys or substitutional alloys. Interstitial alloys means small other atoms trapped inside the crystal, forming interstitial alloys. Substitutional means similar type atoms will go for substitutional alloys. Alloys may be homogeneous solid solution in which atoms of one metal distributed randomly among the atoms of the other. Such alloys are formed by atoms with metallic radii which are within about 15% to each other. The atomic radii differ by 15% each other will form a uniform type of, a good type of alloys. Because of similar radii and other characteristic, transition metals are readily forming alloys. Why these transition metals are forming alloys easily? Because they have similar radius. We have discussed regarding the radius earlier. They are hard and have high melting point quite often. The best known ferrous alloys, chromium, vanadium, tungsten, molybdenum, manganese, used in the production of variety of steels, various ferrous alloys, and in stainless steel. And these are well-known examples, brass and bronze, right? So that is about the alloy formation, right? So various physiochemical properties concerned to transition metal, a talk on melting point, a talk on enthalpy of atomization, a talk on ionization enthalpy, a talk on standard reduction potential, a talk on oxidation state, a talk on magnetic properties and unpaired electrons, colored compounds, complex formation, etc., etc. So many important physiochemical properties, atomic and physical properties and their features connecting to transition metals, right? You must go through all these type of questions also. Now a talk on oxides and oxo anions of transition metals. Oxides and oxo anions of transition metals. Whenever we talk about oxides, we talk about whether the oxide is acidic oxide, basic oxide, neutral oxide, amphoteric oxide, simple oxide, mixed oxide. That is the kind of discussion happening here. You have to review line by line of NCERT to understand various examples being quoted to see whether they are acidic, whether they are basic, whether they are amphoteric. One general point everybody can understand: if an element is giving variety of oxides in variety of oxidation state, a general rule, all of you know, the one with the lower oxidation state will normally be basic. The one with the high oxidation state will normally be acidic, and quite naturally in between can be amphoteric. That is a general feature. General feature. Individually, examples, features, special cases, we must know, right? Let's go through. They are generally formed at a high temperature. All the metal except scandium form monoxides which are ionic in nature. Except scandium, all are forming monoxides which are ionic in nature. The highest oxidation number increases up to manganese. Highest oxidation number increases up to manganese, already discussed in the oxidation number table. The variability in oxidation state increases up to manganese and then decreases, already discussed. Scandium up to manganese. Beyond group 7, no higher oxidation states above Fe2O3 are known. Besides these, there are oxocations. These are some oxocations which are stabilized. Oxocations. As the oxidation number increases, ionic character decreases. That's a general point. When the oxidation number increases, ionic character decreases, acidic nature increases. That is also there. Mn2O7 is a green colored, covalent green colored oil. CrO3 V2O5, low melting point. CrO3 V2O5, low melting point. In these higher oxides, acidic character dominant. That's what I just commented. Lower oxidation state will be pretty more basic in nature. Higher oxidation state, they are expected to be more acidic in nature. Quite naturally, in between, they may be amphoteric. And look at the characteristics. Mn2O7, distinctly acidic as you are getting permanganic acid. CrO3 plus 6 state, giving chromic acid and dichromic acid. Plus 6 state. This is plus 7 state. You are getting permanganic acid. V2O5 is amphoteric in nature, but slight upper hand of acidic character. It is amphoteric with a slight upper hand of acidic nature. V2O5, vanadium pentoxide, giving this kind of salt also. VO4 3 minus, VO2 plus. In vanadium, there is a gradual change from basic V2O3 to less basic V2O4 and to amphoteric V2O5. V2O4 dissolve in acid. That means they are basic. V2O5 react with the alkalis as well as acids, giving two variety of oxocation and anion. CRO is basic, lower oxidation state. CRO plus 2 state, lower oxidation state, basic in nature. While Cr2O3 plus 3 state, in between, amphoteric in nature. That is the general trend commented regarding oxides. So whenever you learn about oxides, try to understand, are they simple oxides or are they mixed oxides? Sir, what is meant by mixed oxide? Let me tell you one IIT question, an old IIT question asking for the oxidation state of hematite and magnetite. Oxidation state of iron in hematite Fe2O3 and magnetite Fe3O4. That's an old IIT question. What is the oxidation state of iron in hematite and magnetite? What is in hematite? All of you know. It is 2 minus here and 3 plus here. It is ferric, Fe3 plus. What about magnetite? What about magnetite? It is 3x minus 8 equal to 0. Therefore, x equal to 8 by 3. That is only average. That is average oxidation number. What is the actual oxidation number? In fact, this is a mixed oxide. And what is the combination of this molecule? This is basically FeO dot Fe2O3. That is what magnetite is. FeO dot Fe2O3. What is the oxidation state of iron? Here it is 2 plus. Here it is 3 plus. So 1 iron in the plus 2 state, 2 iron in the plus 3 state. So the average will be plus 3 plus 3 plus 2 plus 8 by 3. So understanding, see, this is a simple oxide and this is a mixed oxide. So understanding simple oxide, understanding mixed oxide, understanding whether the given oxide is acidic in nature, alkali in nature or basic in nature, amphoteric in nature or neutral in nature. A knowledge on this fact can help you to get a direct question and indirect question also in an examination. Very important point. Hope that is pretty clear to all. Next, an important talk in the chapter is about a very famous molecule. In fact, in the older days of NCERT, we were dealing with a variety of molecules in the total chapter content. But all that been removed from the syllabus. Now we are learning two important compounds in the chapter. All of you know. One is potassium dichromate. One is potassium permanganate. So let's have a talk on potassium dichromate first. Potassium dichromate. That is the first molecule that we are going to discuss in the chapter. Potassium dichromate. It's a very important oxidizing agent. All of you know. Potassium dichromate is a very important oxidizing agent, very important laboratory reagent, very important industrial reagent also. Okay. How it is prepared? It is generally prepared from chromate ore or chromite ore, FeCr2O4. It is prepared from chromite ore, FeCr2O4. Basically mixed oxide, FeO dot Cr2O3, FeCr2O4. That is fused with the sodium carbonate or potassium carbonate. So FeCr2O4 fused with the sodium carbonate in free access of air. You will get an yellow colored product. Sodium chromate is obtained. Yellow colored sodium chromate is obtained. Clear? Now, that yellow colored solution of sodium chromate is treated with acidified with a sulfuric acid solution. It is treated with a sulfuric acid solution. then you will be getting an orange colored sodium dichromate. So sodium chromate yellow in color is switched to sodium dichromate orange colored solution. And in fact, you can crystallize like dot 2H2O. Crystallization is possible, right? But easy crystallization possible when you convert it to potassium dichromate. You will get needle-shaped crystals of potassium dichromate. As the reaction proceeds like this, you get sodium dichromate treated with the KCl. You get potassium dichromate, which is crystallized out as orange colored crystals, orange colored needle shaped crystals. Anybody remember which kind of crystal system potassium dichromate belong to? We are learning in solid state chemistry. We are learning in solid state chemistry which type of fundamental crystal system potassium dichromate belong to. You must know and you must find out. Try to find out. It is the most unsymmetrical crystal system. It is the most unsymmetrical, it belongs to the most unsymmetrical crystal system. Try to figure out which one it is and what are the crystallographic dimensions which you get it as a needle shaped orange colored crystals, potassium dichromate. Okay. So that is what the preparation technique is concerned. And here you can see sodium dichromate is more soluble. That's why we are precipitating as potassium dichromate orange colored crystals. So what are the steps involved in the preparation? Chromite ore fused with the sodium carbonate. You get yellow colored sodium chromate. That yellow colored sodium chromate upon acidification, you get orange colored sodium dichromate. Treated with the KCl solution, you get potassium dichromate crystals. Hope it is pretty clear. Now, this is an important reaction which you must understand in equilibrium condition. The equilibrium existence of chromate and dichromate. There is a equilibrium existence of chromate and dichromate. This is chromate and dichromate. Look at the nature of chromate and dichromate. Chromate is yellow colored tetrahedral system. This is chromate, yellow colored tetrahedral system, and this is dichromate. It is dichromate, two tetrahedra connected. It can be understood like this or you can understand like this. Two tetrahedra connected like this. I remember more than once or even more than 2 times there was question, not in the very old history I am talking, recent history of entrance examination, more than once there was question regarding the bonding nature of chromate dichromate. For example, how many identical chromium oxygen bond present? Chromium oxygen bond, identical bonds, maximum how many are present? It is 6 bonds. You see, these 3 bonds and these 3 bonds are identical. These 3 and these 3 are identical. So there are 6 chromium oxygen equivalent bonds. There is 1 chromium oxygen chromium bond like that. That's a question. And including the molecular dimensions, why can't they ask? The terminal carbon chromium oxygen bond is shorter than the bridged, CrO-Cr chromium oxygen bond, which comes close to 180 picometer. This is just above 160 picometer. So the bond length is different. Bond length is different. These are the 2 forms of chromate and dichromate. One is tetrahedral. The other one is 2 tetrahedral joint. What will be the hybridization? What will be the hybridization? You must think about it. What is the hybridization? Is it sp3 hybridization or something different? All those points we are discussing in our classes. Is it sp3 hybridization or something different? You know, Tetrahedral geometry, it is sp3 hybridization. Think about the hybridization that may happen in chromium, in chromate and dichromate, which are giving one is tetrahedral, one is two tetrahedral connected together. Right? And about the structural details. This is yellow in color and this is orange in color. And they exist under equilibrium. They exist under equilibrium. In acid medium, yellow chromate will be converted to orange dichromate. While in alkali medium, orange dichromate will be converted to yellow chromate. So if the pH is 1, what will happen? In a solution of dichromate, in a solution of orange colored dichromate, if the pH is 1, what will happen? If the pH is 12, what will happen? According to the variation of acidic basic nature, what is the change in color observed and what is the reason? Try to understand. In a high pH, if you are maintaining alkaline solution, yellow color will dominate. If it's a low pH, if you maintain acidic solution, orange color will dominate. So try to go through all those important points, including the structural features of potassium dichromate. As it is commented earlier, it is a very good oxidizing agent. Potassium dichromate is a well-known popular oxidizing agent. So definitely you must go through the oxidizing characteristics, examples, reactions of potassium dichromate. That comes next. You see the potential given for potassium dichromate. This is the potential given for potassium dichromate. Also think about the fact. Potassium dichromate, chromium is +6 state. Potassium dichromate and even dichromate, chromium is +6 state. +6 means all electrons are utilized in bonding. How come they colored? Without the availability of unpaired d electron, if it is d1, d2, d3, d4, it is colored. We already learned. How come this +6 state where all electrons, valence electrons, the 2 electron from s orbital and 1 electron from s orbital and 5 electron from 3d orbital utilized for bonding? All of you know chromium electronic configuration 3d 5 4s1. All 6 electron utilized for bonding. That means it is in fact it's a D0 condition. How come it is colored? You must learn. Okay. You see the potential given by dichromate. Dichromate converted to chromic salt. You are getting E0 value 1.33 volt. 1.33 volt means pretty high positive figure. What is the meaning of positive value? Taught many times in the class. E0 value Cr2O7 2 minus converted to Cr3 plus 1.33 high positive value means this is easily converted to this. This is easily reduced to this. That means it is a good oxidizing agent. So potassium dichromate is in that sense with the quantitative analysis, quantitative idea, we can prove, we can explain it's a very good oxidizing agent as is having very high reduction potential. High reduction potential means high tendency to undergo reduction. Act as a very good oxidizing agent and is able to oxidize. Iodide is oxidized to iodine. Iodide is oxidized to iodine. Iodide -1 converted to 0. Stannous is oxidized to stannic. Stannous +2 oxidized to stannic +4. Hydrogen sulfide, sulfur -2 oxidized to sulfur 0. And ferrous oxidized to ferric, like that. So try to involve studying the various redox reactions involved by the potassium dichromate, including the stoichiometric problems which we are encountering from the concerned area. What is stoichiometric problem? Like many times you might have seen a problem like how many moles of potassium dichromate solution, so potassium dichromate needed for the complete oxidation of 1 mole of ferrous oxalate. Previous question. How many moles of potassium dichromate needed for the complete oxidation of 1 mole ferrous oxalate, like that. So there are variety of stoichiometric calculation questions based on the redox reaction involved by potassium dichromate and in fact potassium permanganate also. So reviewing those problems are also very important, right? Stoichiometric problems. And this is a simple illustration of various species, a few examples, various species oxidized by potassium dichromate. Okay. So that's all about the potassium dichromate. So what important point in potassium dichromate? Let me remind you the preparation of potassium dichromate, the equilibria between dichromate and chromate, structural features of chromate and dichromate, and oxidizing reactions of chromate and dichromate. Okay, next is potassium permanganate. Potassium permanganate, that is the next point. Potassium permanganate, KMNO4, potassium permanganate. Potassium permanganate prepared by fusion of MnO2. Fusion of MnO2 with an alkali metal hydroxide. So MnO2 fused with the alkali metal hydroxide in free excess of air, you get a dark green colored potassium manganate, K2MnO4. K2MnO4, it is manganese in the +6 state. Dark green colored product, potassium manganate is obtained. So basically, potassium permanganate prepared from MnO2. MnO2 in the mineral form called pyrolusite. MnO2 treated with the KOH in free access of air, we get a dark green colored product, potassium manganate, K2MnO4. Now that K2MnO4 with the acid solution, it will be converted to purple colored permanganate. That is what the reaction. And commercially, there can be slight bit of changes. Commercially, how do we do is, this is what a commercial operation which you can see. Preparation of potassium permanganate, MnO2 fused with the KOH, oxidized with the air or potassium nitrate. You get a manganate ion. So MnO2 converted to dark green colored manganate ion. And that manganate ion either by electrolytic oxidation or treating with the ozone or passing with the chlorine. There are different procedures where manganate is converted to permanganate. Manganate is converted to permanganate, giving purple colored solution. So preparation of potassium permanganate, important one, right? Now what comes in permanganate subsequently is its properties and reactions. One more method commended, laboratory method of preparation. Laboratory method of preparation, Mn2 plus interacting with the per disulfate, you can get MnO4 minus. Manganese salt, it treated with the per disulfate, Mn2 plus is oxidized to permanganate. That is a laboratory method of preparation. Try to understand potassium permanganate is dark purple colored crystals. They are isostructural with the potassium perchlorate. They are isostructural with the potassium perchlorate, KClO4. This is the structure of manganate. This is the structure of manganate and this is the structure of permanganate. Manganate and permanganate. Once again, both are tetrahedral. And what will be the hybridization? Is it sp3 hybridization or something different? You must think about it, right? Because we are talking about transition metals, not like a main group element. That's why I am asking. Okay. So both are tetrahedral. This is green colored in nature. This is purple colored in nature and is isostructural with the KClO4. What is KClO4? Cl 1, 2, 3, 4. This is KClO4, ClO4 minus. This is KClO4. They are isostructural. These and these are isostructural. Potassium perchlorate, perchlorate anion and permanganate anion are isostructural. Potassium permanganate, potassium perchlorate. It is isostructural. And the decomposition of potassium permanganate, very important. Potassium permanganate upon heating, +7 state is converted to +6 state and +4 state. +7, it is reduced to +6 state and +4 state. It is converted to manganate and manganese dioxide. Two physical properties of considerable interest. Its intense color. How it is colored. Once again, the question comes, how it is colored? It is +7 state. Manganese oxide electronic configuration, all of you know, D5S2. So all the valence electrons, D and S electrons involved in bonding. Then how come it is colored? Okay, no issue if it is manganate. There is D6. +6 state. One electron can be free there. And of course, it is paramagnetic. Manganate is paramagnetic and permanganate is diamagnetic. No unpaired electron. How come it is colored? You have to think about it. So, molecules like a dichromate, molecules like a permanganate giving a colored nature, that is related to a concept. What is that? You must study and think about how it can be justified. The weak temperature dependent paramagnetism, listen carefully. There is no unpaired electron, but it shows a very weak temperature dependent paramagnetism. And intense color, how it is intense color? How it show weak temperature dependent paramagnetic, usually diamagnetic. These things are something highlight which we should learn as a property related to transition metal. Many times in transition metal compounds and complexes, this kind of observations are being done. Right? NCERT is simply commenting it is beyond the scope of the study. But in fact, the idea regarding that we are studying, try to recollect and find out. I'm not for the time being comment about it. Of course, these things are we are learning in detail in our classes. Right? Once again, potassium permanganate, like potassium dichromate, they are excellent oxidizing agents. They are excellent oxidizing agents. Potassium dichromate also is good oxidizing agent, right? Like potassium permanganate. Potassium, like potassium dichromate, potassium permanganate also very good oxidizing agent, and that reactions. So learning potassium dichromate, potassium permanganate can be done in a similar way. Preparation, structural details, some reactions, and oxidizing action. In fact, you know, the oxidizing action of potassium permanganate need to be discussed a bit more detail, because the oxidizing action is governed by change in pH of the solution. That also is there. You see, oxalate oxidized to carbon dioxide, ferrous oxidized to ferric, nitrite to nitrate, iodide to iodine. These are various reactions, and the nature of potassium permanganate involving the oxidizing action depends on pH of the medium. When there is a change in pH, when there is a change in acidic, alkaline, neutral character of the medium, there is a change in the characteristic of potassium permanganate. You see, potassium permanganate converted to manganate. MnO4 minus +7 changes to +6. Potential is +0.56 volt only. Potassium permanganate converted to MnO2. +7 changes to +4. N factor is 3. Here N factor is 1. It is 1.69 volt. While potassium permanganate +7 changes to +2. N factor is 5. Potential is 1.52 volt. The potential, the standard reduction potential is pretty high in the two cases compared to that of potassium dichromate. Also, you can have a look at that. Greater the standard reduction potential, all of you know, greater the chance for reduction, greater the functioning as a oxidizing agent. So potassium permanganate is a strong oxidizing agent, evident from the standard reduction potential. We can very well see the hydrogen ion concentration plays an important part influencing the reaction. Permanganate, very important point. Permanganate at a pH H plus concentration 1 should oxidize water, but in practice the reaction is extremely slow unless either Mn2 plus ions are present or the temperature is raised. That is a numerical part of the question, came in the recent exams. So practically, what is observed? Theoretically, what can be justified? Potassium permanganate, a strong oxidizing agent. It can oxidize water. Theoretically speaking, it can oxidize water. But when you try to conduct, we see that the reaction is kinetically unfavorable. The reaction is too slow unless there is a catalyst is present or we maintain a higher elevated temperature. Right? Now a discussion on few examples for the oxidizing action of potassium permanganate. Few examples for the oxidizing action of potassium permanganate. Number one, you can see in acid solution. In acid solution, permanganate will be reduced to Mn2 plus. Permanganate plus 7 will be reduced to Mn2 plus. That will be a common point. And here you can see iodide is oxidized to iodine. Number one. Ferrous is oxidized to ferric. In all the cases, permanganate will be reduced to Mn2 plus in acid medium. And what is the N factor? What is the N factor? N factor will be 5. N factor will be 5. Quite naturally, the equivalent mass will be molar mass by 5. Equivalent mass in this case, that is in the acid medium, where permanganate is reduced to Mn2 plus, the equivalent mass will be molar mass by N factor, molar mass by 5. How it is N factor 5? Plus 7 changes to plus 2, that is N factor 5. More examples followed by, have a look at this. Oxalate oxidized to carbon dioxide. Oxalate oxidized to carbon dioxide. Oxalate plus 3 state oxidized to carbon dioxide plus 4 state. Sulfide oxidized to sulfur. Sulfurous acid or sulfite oxidized to sulfate. Sulfite plus 4 state oxidized to sulfate plus 6 state. Nitrite oxidized to nitrate. Nitrite plus 3 state oxidized to nitrate plus 5 state. Like that. There are so many such examples. And here also I would recommend and I would strongly suggest you must go through the stoichiometric problems concerned to this area. Not over. What happens in neutral medium or faintly alkaline medium? Neutral medium or faintly alkaline medium. What is happening in neutral medium or faintly alkaline medium? See, here permanganate is reduced to MnO2. Permanganate plus 7 is reduced to MnO2 plus 4. So what is the N factor? Plus 7 to plus 4. N factor equal to 3. Therefore, equivalent mass is equal to molar mass by 3. That will be the nature of N factor when you take in neutral medium or faintly alkaline medium. Now what is the reaction? Reaction also slightly changing. You see, iodide is oxidized to iodate. Iodide minus 1 oxidized to iodate. Iodate is plus 5 state. So iodide converted to iodate plus 5 state. What is the N factor? Minus 1 to plus 5. 6 is the N factor. Like that. Thiosulfate oxidized to sulfate. And Mn2 plus oxidized to Mn4 plus. Mn2 plus. Here you can see plus 7 and plus 2. converted to +4. Two different oxidation state coming to one state. I think all of you heard about it. Is the so-called yes, +7 coming to +4 state, that is reduction, +2 going to +4 state, that is oxidation. Somewhat opposite to disproportionation, many of you may be aware of the so-called syn proportionation or com proportionation. I think many of you are aware of. This is an important point. This is an important point. When we say acidified potassium permanganate, many times we use the term KMnO4 in acid medium. KMnO4 in acid medium. Acidified potassium permanganate. Which acid is used for acidification? Is it sulfuric acid or hydrochloric acid? In acidified potassium permanganate, which acid is used? Is it hydrochloric acid or is it sulfuric acid? The answer is sulfuric acid. So this acidification can be done by sulfuric acid, not by hydrochloric acid. This cannot be. Why HCl cannot be? Permanganometric titration in presence of hydrochloric acid are unsatisfactory since hydrochloric acid is oxidized to chlorine. Hydrochloric acid will definitely help you to maintain the pH, no doubt. But the problem is hydrochloric acid contains Cl minus. It is a reducing acid. And the Cl minus from hydrochloric acid will interfere in the reaction. I think majority of you know this fact. Acidification of potassium permanganate, acidification of potassium dichromate, it won't give you a satisfactory result with the acidified with the hydrochloric acid. It has to be acidified with the sulfuric acid. Okay. So that is about the two important compounds dealt in the chapter potassium permanganate and potassium dichromate. Next is inner transition elements, F block elements. Inner transition elements, F block elements. All of you know, already discussed, there are two series, lanthanoids and actinoids, coming as a continuation of lanthanum, 14 elements, lanthanoids. See, coming as a continuation of lanthanum, which is in the third period, scandium, yttrium, lanthanum, actinium. So scandium, yttrium, after lanthanum, 14 elements which are available in the 4F arrangement, 4F electronic system called lanthanoids. They are also called 4F series. And then the second one is actinium series. All of you know actinoids, 5F electronic configuration. Lanthanoids are starting from 58 cerium up to 71 lutetium. 58 cerium up to 71 lutetium. Cerium, praseodymium, neodymium and promethium. Promethium is radioactive in nature. Among that line, only one radioactive element, promethium. Samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, thulium, ytterbium, lutetium. That series you have to by heart it. Why? Because couple of times there was question regarding the order of ionic size. We know there is a lanthanoid contraction. And based on lanthanoid contraction, they ask a question. What is the order? So to arrange that correct order, you must know the order of elements. While 89 actinium up to 103 lawrencium, they are actinoid series of elements, which we are learning about in the inner transition elements. As all of you know, the electronic configuration already commented. The electronic configuration comes out to be for the transition, inner transition elements. How is the electronic configuration? A noble gas core, N-2, F 1 to 14, N-1, D0 or 1, Ns2. This is the electronic configuration of the F block series. and electronic configuration happening over here in the f orbital. And there are two series, 4f configuration happening lanthanoids and 5f filling occurring actinoids, right? So let's go through lanthanoids in detail. Lanthanoids, the symbol used is Ln. Lanthanoids, the symbol used is Ln, and this is lanthanoid contraction. The diagram 8.6 tell you lanthanoid contraction, a gradual decrease in the atomic ionic size, especially ionic size. In atomic size, except one element, that also giving a gradual decrease. You see, a gradual decrease in the atomic and ionic radii as a result of increased nuclear charge. Step by step, as you proceed from cerium to lutetium, there is a step by step increase in the effective nuclear charge. Why? Because each time when the proton increases, electron increases, electrons are added to f orbital. And all of you know the problem with the d and f orbital. D and f orbitals are having poor shielding effect. So due to poor shielding effect of d and f orbital, particularly f orbital to which the electrons are filled up, there is a gradual increase in the nuclear charge. So the gradual upper hand in the nuclear charge causes decrease in size, gradual decrease in size, which we call it as lanthanoid contraction, and is beautifully demonstrated in the graphical representation. When you start from lanthanum, then cerium up to lutetium, you can see there is a regular gradation in the atomic ionic radii. This is called a lanthanoid contraction. And what are the important properties of lanthanoid contraction? What are the important, not a property, consequence of lanthanoid contraction? That also is many times came for exam. Lanthanoid contraction is the basic reason. Lanthanoid contraction is the basic reason why the size of this series, 3D series, 4D series, atomic size is considerably different. We have discussed that. Few minutes back we have discussed in the class. The size of this and this are considerably different. But the size of this and this are very close. Why? Because, see, when you move from here, when you move from lanthanum to the 14 elements, the electrons are filled in f orbital and there is lanthanoid contraction. And after lanthanoid contraction, you are coming back to 72 hafnium, tantalum, tungsten, rhenium, osmium. So what happens? This will be consequently affected with the lanthanoid contraction, and the size of these elements which are followed by lanthanoid contraction, quite naturally their size will be lower than what we expect. So this is an important property. Among the three transition series, 3D, 4D, 5D, 3D, 4D has a good difference in the atomic size. While 4D, 5D, their atomic size is very close, maybe differing by 1 unit above or below. And that is a consequence of lanthanoid contraction, all of you know. Another consequence of lanthanoid contraction is as you proceed from cerium to lutetium, what is the nature of hydroxides? You can see the nature of hydroxides, the basic strength decreases. The basic strength of hydroxides, lanthanoid hydroxides, decreases as you move from cerium to lutetium. That is another important consequence of lanthanoid contraction. These two consequences which already appeared for the old exams. You must go through that. This is a typically lanthanoid contraction due to poor shielding effect of 4f electrons in lanthanoids. Of course, there is an actinoid contraction in 5f actinoids. This, in fact, is a very important paragraph, I would say, from NCERT regarding the properties, oxidation number, and characteristics of lanthanoids and their compounds. You see, La2 and Ln3, normally their oxidation state is +3 state. Lanthanoids are well known for their +3 oxidation state. Their predominant oxidation state is +3 state. However, occasionally plus 2 plus 4 also found in solid state or in solution. The irregularity arises, the irregularity as in ionization enthalpy arises. This is also very much known. The empty, half-filled, fully filled orbitals will be stable. All of you know. Empty f orbital means the inner core is full. Half-filled will be always stable due to exchange energy concepts we know. Fully filled is also stable. So many of the oxidation state coming across because of the empty, half-filled, fully filled substance. Cerium 4 favored by noble gas configuration. Cerium 4 favored by noble gas configuration. But it is a strong oxidant. Look at the reduction potential 1.74. Cerium 4 plus 3 plus. Cerium 4 plus 3 plus. The potential is 1.74. That means cerium 4 plus will be easily oxidized, reduced to cerium 3 plus. That's a general point. Lanthanoids usually maintain plus 3 oxidation state. So cerium 4 plus easily will be converted back to cerium 3 plus. That means easy reduction, it acts as a good oxidizing agent. And again see that it can oxidize water. Theoretically, it suggests cerium 4, cerium 3 can oxidize water. Cerium 4 plus can oxidize water. However, the reaction rate is very slow and hence it is a good analytical reagent. Potential question: why cerium 4 solution act as a good analytical reagent? Why not? Because theoretically it can oxidize water. Anybody can oxidize water. How can it act as a good analytical agent in aqueous solution? Cannot. But it is. Why? Because maybe theoretically it can oxidize water, but practically unable to, as it is giving the rate of reaction is too slow. It is kinetically unfavorable reaction. Kinetically unfavorable reaction. There are many people who exhibit plus 4 state. All plus 4 state will be oxidizing agent. All plus 2 state will be reducing agent. Europium 2 plus. Europium 2 plus obtained because of F7 configuration. But it is a strong reducing agent. Why Europium 2 plus is a strong reducing agent? Not only Europium 2 plus, anybody 2 plus can act as a good reducing agent because they want to go to plus 3 state. The stable oxidation state is plus 3 state. So if it is in plus 2, will go to plus 3, undergoing oxidation, act as a reducing agent. If anybody in the plus 4 state will come back to plus 3, will undergo reduction, act as a good oxidizing agent. So normally speaking, a species in the plus 4 state here will act as a good oxidizing agent. A species in plus 3 state here will act as, plus 2 state here will act as a good reducing agent. Because plus 4 will come back to plus 3, plus 2 will come to plus 3. So they will act respectively as good oxidizing agent and good reducing agent. You see, terbium 4 act as a very good oxidizing agent like that. This is a table explaining the electronic configuration and their atomic size and all. Electronic configuration, atomic size and all. You must go through the configuration. I think many times you might have noticed and even discussed in many classes. Gadolinium, GD electronic configuration appeared more than once for the exam. GD configuration. GD having 4F7, 5D1, 6S2. Like that, any other species which may be encountering, you can analyze. Lutetium, F14, F14D1, F14D1S2. Europium, F7, 6S2. Europium 2 plus, F7. Terbium 4 plus, F7. Sir, why F7 you are highlighting? You know, F7 is half-filled system. F14 is fully filled system. F0, F7, F14, they must be important, right? This is contraction. You see the contraction? You see the contraction. At the same time, keep it in mind. Keep it in mind. One person is out. Who is that? Europium. Europium in the elemental state, non-ionized state. The size is not in match with the gradual decrease. 187, 83, 82, 81, 199. But that is not observed here. Here there is a regular gradation. So lanthanoid contraction is well maintained in the ionic state, and one exemption, europium, in the atomic state. Make a note on. Sir, this much meticulous? Yes, you have to. You have to. This much meticulous, you have to. No other way. Look at the general properties. They are silvery white, soft metals, tarnish rapidly in air. Hardness increases with increase in atomic number. Samarium, steel hard. Melting point will be in the range of 1000 to 1200, while samarium 1623. Trivalent lanthanide ions are colored both in solid state and in aqueous solution. A statement based question in the latest, the recent history of NEET exam and various other exams. La3 plus, lutetium 3 plus does not show any color, because to show color there must be some unpaired electronic system. So F0 cannot may not perform color. F14 may not perform color. You see this is F0, this is F14. The others are paramagnetic in nature. The lanthanide ions other than this, lanthanum 3 plus, cerium 4 plus, F0 type, ytterbium 2 plus, lutetium 3 plus, F14 type. All others are paramagnetic in nature, while this is diamagnetic. No unpaired electron. So first ionization enthalpy around 600, second around 2200, comparable with the calcium. You can see many of the properties of the starting members of lanthanoids. It is similar to calcium. As you move right, it is more similar to aluminium. Like that. It is there. Earlier members similar to calcium, while the later on it is more like aluminium. You look at the standard reduction potential. The standard reduction potential is high negative. Standard reduction potential is high negative. You see that minus 2.2, 2.4. That means they are good reducing agents. They are good reducing agents. They are active metals like S block. Like S block elements, they are active metals. These are the various reactions compared in lanthanoids. Lanthanoids can give you Ln2O3 like aluminium. It can release hydrogen treated with acids. It can form LnX3 like aluminium. It can form LnOH3 liberating hydrogen. LnC2 carbide at high temperature. Lithium nitride like ALN aluminum nitride. You see, many of the molecules formed, many of the product formed is quite similar to aluminium, isn't it? It seems to be like that. They form oxides M2O3 and hydroxides MOH thrice. They are definite hydroxides, definite compounds, not just hydrated oxides. They are basic. They are basic. When you compare with the aluminum hydroxide, don't compare the characteristics. Aluminum oxide is amphoteric in nature. Lanthanum oxide is basic in nature. Very important point. The later members of lanthanoids are similar to aluminum. Yeah, fine, good in the formula, but may not be in the characteristics. Aluminum hydroxide is amphoteric in nature, while these are basic in nature and quite reactive, similar to S block elements. A very important talk is about some alloys formed by lanthanoids. They form important, very popular mischmetal alloy. Mischmetal consists of lanthanoid metal approximately 95%, and iron 5%, traces of sulfur, carbon, calcium, aluminium, etc. Mish metal used in producing bullets, shells, and lighter flints. Many catalyst in petroleum industries and all. That's about lanthanoids, right? A small talk on actinoids is what left in the chapter. This is about actinoids. The members are actinium, starting from 89 actinium and continue with the 5F series: thorium, proactinium, protactinium, uranium, neptunium, the deadliest element, plutonium, the deadliest element, americium, curium, berkelium, californium, einsteinium, fermium, mendelevium, nobelium, and lawrencium. All these are radioactive elements. All these are transmuted elements. All these are probably called transuranic elements. Transuranic elements derived from uranium. Here also you can find some configurations like this, which you may kindly make a note on to, which there is a possibility F7 systems and F14 systems, like that. We can predict how they're going to ask. Here also there is a contraction, actinoid contraction. There is contraction, but no much of the chemistry like lanthanoids. No much of chemistry like lanthanoids, because you know many times they are prepared in nanogram quantities. So it's not the chemistry is not that much prominent. Electronic configuration already we have seen. Ionic size, actinoid contraction already we have seen. A very important point is oxidation state. Oxidation state. Look at the oxidation state of actinoids. Isn't it quite similar what you find in the transition elements 3D series? The variability in oxidation state increases, comes to a maximum, and then decreases, like that, right? Somewhat similar to the earlier table seen for transition elements, isn't it? You see maximum variability performed by neptunium, plutonium, and in fact, in the recent history of entrance examination, the oxidation state of neptunium, that was a question. It is from 3 to 7 continuous, 3, 4, 5, 6, 7, like that. They perform more variability in oxidation state. And why there is a, you see, there is a greater range of oxidation state which is attributed to the 5F, 6D, 7S or comparable energies. The comparable energies of orbitals, reason for variability in oxidation state, but still not much of important because much of the chemistry is not dealt. They are all silvery in appearance. Highly reactive, especially when finely divided. The action of boiling water, example, mixture of oxide and hydride. Combines with most of the non-metals taking place at moderate temperatures. Hydrochloric acid attack all metals, but most of slightly affected by nitric acid. No action on alkalis. So 3 important points come under reaction with hydrochloric acid, just like active metals. So they are active in nature. So they are highly reactive metals, number 1. Number 2, no much action with the nitric acid. Why? They are rendered passive. Like what happens in beryllium, like what happens in aluminium. Aluminium rendered passive with the concentrated nitric acid, like that. And number 3, no action with the alkalis, as they themselves are alkaline in nature. Magnetic properties, no much of discussion because it's more complex. Their ionization enthalpy is expected to be lower than compared to early lanthanoids. The 5F orbitals, they will penetrate less into the inner core. 5F orbitals are more available to the periphery of the atom. Therefore, they are more interacting with the environment. Very important point. That's all. That's all from the aspects of lanthanoids. And please verify some important applications in D and F block elements. Of course, there will be some reasonable good points like titanium oxide used in pigment industry, white pigments, MnO2 used in dry cells and batteries, zinc, nickel, cadmium in the battery industry, coinage metals, old idea, coinage metals, gold, silver, etc. Terms like UK copper coins, silver UK coins, etc. Vanadium pentoxide, preparation of contact process, already commented. This is an important point. This is an important point. Ziegler-Natta catalyst. Ziegler-Natta catalyst. Titanium chloride and trialkyl aluminium. Titanium chloride and trialkyl aluminium used as Ziegler-Natta catalyst in the manufacturing of polyethylene, polythene. This already all of you know, Haber process, iron using. This is another process, another important one. Wacker process. Wacker process. Oxidation of ethane to ethanol catalyzed by palladium chloride. Wacker process. Wacker process came for exam multiple times. Is not dealt in organic reactions. It is not dealt in organic reactions, but the question came from this area. That's all. That's all. And there we conclude one of the important chapters from the 12th standard area, D and F block elements. When you go through the NCERT also, the linguistic representation of NCERT, slight bit of the traditional NCERT language. So we have to read the lines carefully. Sometimes we have to think in between the lines or behind the lines also to understand the concept perfectly. Anyway, there are so much important aspects which we can find regularly coming for the exams. Try to go through the previous year question papers as much as possible to identify the important part of the discussion. See, you can't exempt any single line from the NCERT as far as the questions coming are concerned, particularly NEET exam. Of course, if you go to JEE advanced questions, it can be mainly conceptual based, and I mean, there can be simple question, but at the same time, they may ask for the numerical type or problems based on some application type questions also when you go through the JEE advanced exams are concerned. Some comprehending type, narrative type questions also, right? Anyway, pretty long chapter. Please go through thoroughly. And there we conclude the chapter D and F block elements. In another video, we will meet with another chapter. Till then, bye. See you. Take care.